Okay, so today we will be covering some digital signal processing, everything you'll need to know if you would like to do a digital audio visualizer. Sign-in link is there if you're actually in person, and hopefully you got it. Okay, so some quick announcements. You guys should be done with labs 1 and 2 by now, for real, for real. But if you haven't, just let us know. Reach out to us if you need any help, of course. Hopefully we'll make things a lot smoother for you. And yeah, so I've already done that, so perhaps I'll do it again and check in on everybody. And then yeah, hope lab 3 is going well. I have seen some people already start to finish them, so that's wonderful to see. Lab 4 will be released shortly, once again in the DAV links as always, and this is the final lab, so you guys can do it. End is here. We'll be hosting another work session next Wednesday, as well as the week after that, in Bolton Hall 5800. Sorry, things have been kind of messy recently, but it will be there from 6 to 8 p.m. Next week and the week after. Yeah. Um, so finally this quarter, hopefully you've kind of thought out some ideas for your capstone. So feel free to reach out to us whenever you have an idea and schedule a quick meeting. So this is particularly if you want to do some fun experimenting with because potentially if you want to do like a new controller or something, you might need like new parts and we can help you out with ordering that for you. So be sure to reach out if that's something you're interested in with. And in really fine text in the bottom, because I don't really like want to say this too loudly, but even if you haven't finished all your labs, it's good to start thinking about your capstone. We don't want the labs to be a barrier, but obviously the labs are extremely helpful in actually finishing your capstone. So do the labs, but also start thinking about your capstone. Another thing is officer info session. So elections are coming around. They're going to be the start of spring quarter. Um, we will have an info session February 25th, 6 p.m. in the Cohen room. I didn't put down the room number, but you guys can find it. So come in, you'll hear everybody talk, whether it's for Dav or for another position, you guys should run. It's really fun being on the board. You get a lot of experience, get to meet new people. Um, this officer info session will also be a little bit more interactive. We're trying to do like speed dating or whatever, so you'll actually get to talk to the leads, kind of see how the application process will go, get some inside information. So it'll definitely be useful if this is something you'd like to pursue, which I suggest to everybody. Um, yeah, even if you're not like super confident, I don't think me or Jonathan were like super like 100% knowledgeable when we started. We learned a lot as we go, so be sure to just give it a try. It's a good experience, no matter what happens. Yeah.
Yeah, so that's all of the announcements that we wanted to make. Now we're going to go into today's lecture, which is in digital signal processing. Before we go into that, I'm going to go over the two main ways that we're going to represent signals or like other information, which is one, the time domain, and two, the frequency domain. So the time domain is where we represent signals, where with the x-axis is the time, and the y-axis is the amplitude or like how loud your signal is. Frequency domain, we change the x-axis to be represent the frequency, and the y-axis is still the amplitude or the loudness of the signal. So we're used to seeing signals plotted as a function of time. In many cases, like in math classes or in other classes, they're usually just like sine waves or maybe like something a little more complicated. In practice, though, we capture far more complicated signals. And so it's actually really hard to decipher any of the information within much more complicated signals in the time domain. And so here's an example of a signal with just three frequency components. So what that means is we have three different sine functions all added up together to form this final function here. And so this is quite complicated if you just look at it from the time domain. But as you'll see in a later slide, it's a lot easier to understand what's going on here in the frequency domain. Here's another example, which is just like a basic speech signal of like maybe a human voice. This is in the time domain. From here, you can't really tell what's going on, But if we transfer this into the frequency domain, it's going to be a lot clearer. And so, yeah, this is why we're interested in the frequency domain. Many times the frequency spectrum of a signal is a lot easier to interpret than the time domain of the signal. So here is the spectrum for a sine wave at hertz, or like any variable hertz. The horizontal axis, as I said earlier, is the frequency instead of the time. And the vertical axis is the amplitude, which just represents how loud the signal is. And note that the sine wave has a positive and a negative frequency component, and this is just because we represent sine waves using Euler's formula, and that has a positive and a negative component. However, I'll mention later that we don't really care about the negative component because the negative component is usually a mirror of the positive component when we're dealing with real signals. So if you look at the cascade, like of the summation of a bunch of sine wave signals earlier, if we break this down into the frequency domain, you'll see it's a lot clearer. So here, this function consists of 3 different frequencies. One is at 1 hertz, one is at 2 hertz, and one is at 4 hertz. This is a lot easier to read. So this is a very basic example of why we want to represent signals in the frequency domain as opposed to the time domain. For more complicated signals, you might get a frequency plot that's a lot more complicated like this. Most of our signal is contained within a range of frequencies, and we call that the bandwidth. And so basically what this lecture is going to be is how we're going to transform signals in the time domain, because we're sampling signals in time as opposed to frequency, and how we're going to be able to transfer that from the time domain into the frequency domain. And all of this is going to be related to the Fourier transform, which Gerard will talk about later. And also, as I stated earlier, we'll only consider positive frequencies from now on, because for our signals of interest, the amplitude spectrum is even, which means that all of the negative signals are a mirror of the frequency to frequency. Sorry, all of the negative frequencies are a mirror of the positive frequencies, and so we can essentially just ignore the negative ones.
Okay, so not yet. Okay, yeah, so we're just gonna go over digital analog signals. So really quick, basically real world signals such as radio waves, sound waves, which is primarily what we'll be working with, as well as voltages in a wire are analog signals, which are continuous in nature. So continuous means that it will take on values at all points in time, as well as analog means it can take on any possible value. Yeah, so what that means, is basic. I guess I'll talk about later, but in practice, we can use analog circuits to kind of amplify, filter, and mix them, which are useful for a lot of things that we will not really be discussing because that's actually part of a different project called RAP, and that's some fun stuff if you want to dive into that. But what we will be working with is going to be a digital signal. So why don't we just work with the analog signal? Well, as you can imagine, with it being taking on infinite amount of values in time, as well as infinite possible values, we can't really do that because we have finite storage and finite resolution in our computers. So we can't store every single value. It's just not possible. However, we do want to maintain our signal and to understand what it is. So we represent it using a digital signal. So what is a digital signal? A digital signal is basically a sequence of numbers. So this sequence of numbers will dictate kind of what your signal looks like. And then along with this sequence of numbers, you must know which sample is at time 0, as well as our sampling frequency. So the sampling frequency dictates how often your signals occur. So for example, if I had a sampling frequency of like 1 hertz, that means we're taking 1 sample per second. So that means, like, for example, if my x0 was a 0, x1 was a 1, and so on, what we'd see is a 0 at 0, a 1 at time 1, a 2 at time 2, and so on. And then we also need to know which sample is going to be at 0. So understanding the sampling frequency and the time 0, as well as the actual values, we'll be able to reconstruct a digital version of our signal. We will also be keeping the sampling frequency consistent throughout the signal. It's not going to change or anything. So there's just one sampling frequency. So the next question is, what is the sampling frequency? How fast should we sample signals? So for example, a sine wave. Um, so basically, intuitively, the faster we sample a signal, the more information we will receive. So as you can imagine, if we sample faster, we'll get more samples, we'll see more of the signal. However, with more samples of the signal, it's more storage, more processing. So there's definitely trade-offs. So what we've defined is a minimum sampling rate. So the minimum sampling rate is going to be two times the maximum frequency present in a signal. So basically what this means is that the Nyquist rates, um, for example, if I have a signal that's 5 hertz, that means my sampling rate will need to be at the minimum of 10 hertz in order to perfectly sample the signal. So as you can see on the left is a signal that does not follow or does not keep up with the Nyquist rate. So we sample at a rate slower than two times. As you can see, although we get our samples from this initial sine wave, when we only look at the samples we took, it's actually reconstructed incorrectly since it doesn't give us enough information. On the right-hand side is the Nyquist rate reconstructed perfectly from the samples. That's what we love to see. Yeah, so if you sample too slow, basically what will happen is something known as aliasing. So what this means is that with these samples, you see a different signal that is possible, which is the alias, and that's not good. Um, kind of a high level overview kind of is like basically sampling creates copies of the signal spectrum, and the faster we sample, the more space will be in between each copy in the frequency domain. So basically when we're sampling, if you've done some like 102, is basically we're going to multiply the um the signal by an impulse function at certain periods of time. And then basically, if you do some more, if you know 102, when you do the Fourier transform, it'll basically create replicas, and then where they are will be based off of your sampling frequency. And then if your sampling frequency is too small, they'll be too close together, they'll start mixing and becoming aliased. Um, but yeah, just know that to abide by these Nyquist rate rules, that's kind of the general idea. Um, Real quick question, because I feel like it's, for example, like if I had a cosine 10 pi t signal, what would the minimum sampling rate be? I didn't write it down, so I'll say it one more time. Cosine 10 pi t. Go for it. I believe it would be 10, right? Because 10 pi for cosine it would be equal. Yeah. So 10 pi is equal to 2 pi times the frequency. So that means the frequency is equal to 5 for that sinusoid. Multiply that by 2, it would be 10. So yeah, just some practice. Yeah. All right. So the next section we'll be diving into some 113, actually not even 113 stuff, but we're gonna be doing the discrete Fourier transform. Hopefully you guys can follow along. 102, 113 definitely help, but yeah. So basically, oh, all right. There are two main kinds of transforms that are useful. So the first one here is the Fourier transform. So the Fourier transform is for analog continuous signals. So basically, we won't really be working with it, or I guess we'll start the derivations from there. But it's for continuous analog signals. What you're doing is you're multiplying by a complex number. This complex number has a W value, which is basically the frequency component. So what you're doing is you're multiplying your signal by a complex number at certain frequencies, and basically the resulting multiplication will give you how much that signal, um, how much that frequency is present in your signal, and then you integrate it to combine it all together, and that'll give you your frequency domain like representation of your signal. So yeah, and then for reference, x of t is the time domain signal that we're looking at. And then x of w with the capital is going to be our frequency domain representation. And then the next thing is going to be the other useful transform is going to be the discrete time Fourier transform. So what this is, it's basically the Fourier transform, but for discrete digital systems, or I guess just discrete systems. So for this one, instead of a continuous x of t, we instead represent x of n being our sequence of number we showed you earlier. And it follows the same concept of multiplying by a complex number at different frequencies and then finding out how present the frequencies are. Yeah. Um, so something to note, if we have a periodic signal, we can write it as a Fourier series, which is a set of numbers that completely describes the signal, which is what we would like to do. Because basically what we want to do is we want to create a frequency domain representation of the signal, which a prerequisite of that is the representing it as a Fourier series, which allows us to do the whole sequence numbers with a sampling rate representation. However, this is a problem. The reason behind this is that periodic signals are going to be infinite in time. And when you're talking to your digital audio visualizer, you're not going to be sitting there for an infinite amount of time. So it's not possible to create a like fully periodic infinite signal. So instead, what we're going to be working with is finite length signals. And we can use the discrete time Fourier transform to do this. Um, However, there is also an issue with this. Maybe I should have included an image, but basically, there are Fourier transform pairs, and there's of course discrete time Fourier transform pairs as well. And basically, in general, when you have a finite signal in the time domain, you will have an infinite signal in the frequency domain, and vice versa. So infinite signal in time domain, finite signal in or frequency domain. So our goal currently is to input a um a finite signal into our DAV, our audio visualizer, and then also view a finite frequency domain representation. However, from our two different types of transforms, that's not possible because they're infinite, and we can't represent infinite values. So instead, we are going to derive something different called the discrete Fourier transform. So um, for this, we'll kind of be showing it through an example. This is our example signal. So it has four samples, 0, 1, 2, and 3. And yeah, so we can't take the DTFT for the signal because it would be continuous in frequency. So instead, we're going to do something called periodic extension. And then just to like reaffirm this whole idea, if you know your Fourier transform pairs, like for example, like the rectangle function, if you take the Fourier transform of that, it will become the sinc function, which is infinite in time. So we want to avoid having something infinite. So by doing periodic extension, we basically have our finite signal and turn it into an infinite signal. So in here, the orange represents what we started with, and the rest is extended. So as you can see, it's periodic in nature. The same four samples are repeated over and over again. So yeah, our resulting symbol is periodic. For discrete signals, this means we will be able to write it as a Fourier series. And the Fourier series is a sum of sines and cosines. Um, which will basically allow us to represent our signal. Um, this is an example of what our x of n looks like, but yeah, basically it's just a summation of cosines and sines at different frequencies, and that allows us to reconstruct our signal. So, as you can see here, we have two different summations, one of cosine and one with sine. However, we're going to simplify this using Euler's formula. So e to the power of jwn, where w is our frequency component and n is whatever indexed sample we're looking at, has some cosine sine representation like this. So if we just take this equation and replace it with the Euler's formula, we now have this smaller, nicer to look at equation. So looking at it, C with subscript K is basically going to dictate like what values we have. So this will be kind of just arbitrary. But then we see this e to the power of j w subscript k n, and this frequency component we don't really know what it means quite yet. Yeah, so we're gonna go over that. So as you can see, as I said earlier, basically the same four samples in our example are repeated over and over again. If we had like 10 samples repeated over and over again, n would be equal to 10. But basically, x of n is equal to x n plus 4. So you can see at x of 0, it's like halfway through, and then 4 of the little things later, it's at the same value. So that means the fundamental period is 4. So every 4 samples, it will have the same value again. So basically, when we write this as a sum of periodic functions, each of the functions must repeat itself after 4 samples, regardless of what happens in between. And this will be important when we talk about like which frequencies we need to represent and which ones we can ignore or just won't be there. So basically, we're going to just try this expression for for w subscript n. So the expression is going to be 2 pi over n. So if you remember, n is our fundamental frequency, and w is typically 2 pi f. So it's just basically just using that. And then we also have k. So basically, we're going to have 2 pi over n, our fundamental frequency components, and multiply it by k. K is going to be like our harmonic number, which it's just like it's just a number. It's there. So basically, with this expression, we can substitute in n equals 4 into our equation. So substituting that in and multiplying it out, we get two different expressions, e to the j 2 pi k n, which basically will always equal 1 because what you end up getting is cosine to the power of 2 pi kn, which is 1, plus or minus, or no, plus sine of 2 pi kn, which is 0. So you'll always get that first value equals 1 is equal to j to the 2 pi over 4 kn. So multiplying that last value by 1 gives you the same value. And this kind of equation at the bottom here tells us and proves that our signal using this W is periodic in nature over with a period of 4. As you can see, the n equals 5 is equal to, sorry, n plus 4 is equal to the 1 at n. So it's periodic in nature. Are there any questions so far? Does that make sense? Okay, cool. Yeah.
This mean that this can retain on values of like plus or minus 1 and plus or minus j.
Um, Wait, sorry, say that one more time.
Because are both of these, like K and N, they are both integers, yes.
Yeah.
So does that mean that like when you plug in this N sign, like using the same logic that you guys said, say that stuff is equal to one?
Yeah.
Like we can say it's equal to either one, -1, J or minus J.
Well, for example, if our K were to be okay, let's just say our N was uh like 3 or something, then it wouldn't be 1, -1 or 0, but it would be like, oh my gosh, unit circle. It would be some other value other than -1 and 1. But we just use 4 because it's nice and convenient. Um yeah.
J is imaginary. It's like I, we represent. Yeah, it's not like a variable.
I mean, like, the thing with the value, like, it needs to let
Oh,
you develop it to like 1 - 1 J or minus J.
it depends on like the capital N. It depends on like how big your
Oh wait,
force
sorry.
is. Yeah.
Basically this N will always cancel out because the N plus, because you see we're doing N plus 4. Maybe we should have done this with in like variables, but it's basically N plus capital N, and then the W is 2 pi over N, big N. So it's just N over N, so it'll always cancel out no matter what the N is. So it'll always be equal to 1 there. Okay. Yeah, any other questions? Yeah. Would be nice if I could write things out, but I kind of forgot my adapter. That's okay. Um, yeah. So yeah, so now we now know what our W subscript K is equal to, and we substituted it in there. So yeah, cool. However, as you can see here, what we're doing is we are going through every single possible harmonic from K -infinity to infinity. However, that's not very necessary. So the only harmonics we need to go over is 0 to K equals N minus 1. And this may seem kind of strange because we aren't looking at a lot of the frequencies. And the reason for this is I will explain. But basically, as you can see, we have two different signals. One is cosine 2 pi over 4 t, one is cosine 2 pi over 4 5t. So they are different by um, like 4 harmonics. Um, Currently, we have uh, n is equal to 4. So if you see our point at 0 and our point at 4 are the same. But you can also see that our points, if we line them up, are the same at every single point between these two harmonics. So these two harmonics are representing the exact same thing. So it isn't really necessary to have both of the harmonics represented when we try to reconstruct our signal. Yeah, any questions on that? Does that make sense? Okay, cool. Yeah. So now that we know our periodic extension can be captured by just that portion based off of our fundamental period, uh, we can now derive our DFT. However, basically, what we've actually been doing this whole time is trying to reconstruct our original signal from the frequencies we've had. So we've actually derived the inverse discrete Fourier transform instead. Um, yeah. So if you know Fourier transform like pairs and stuff, they are actually quite similar in nature. The big difference is that you just kind of throw in a negative there. And then for the discrete Fourier transform, It is also averaged in time the um for the inverse, and then it's not for the frequency one. Um, Truth be told, I might need to sit down and figure out why that is. But yeah, so the left is the discrete Fourier transform, the right is the inverse discrete Fourier transform. And that's basically what we're going to try to implement. So we're going to receive some kind of finite voice signal from our microphone. We're going to pass it through an analog to digital converter, and then we're going to pass it through our discrete Fourier transform, or not quite yet, but the same idea. And that'll give us a finite Fourier or finite frequency representation of our signal. Yeah. Does anybody have any questions? I know I went through that kind of fast. Okay, cool. Oh yeah. So I guess yeah, once again, finite length frequency for a finite length signal. We basically use this trick of copying our signal to infinity. And yeah. Well, there's more. Oh, there's a lot more. Okay, never mind. Absolutely. Okay. So another thing to know, oh right, this part. So we also will split the frequency range from 0 to our sampling rate. So basically how this works is that we're not going to be representing every single frequency. As you remember, our values are not going to be, yeah, go ahead.
So the reason why we don't take the sum to infinity because like you only need one time period and that without one time period like tells us all the frequencies in R. So that's why it's like only the first like the n terms in the sum the n for the n samples.
So are you saying like why there's a 1 over n here?
Yeah, so I'm asking like before the summation was taken from minus infinity to infinity.
Right,
But now we're taking it from 0 to n minus 1.
right.
Is it because that the signal from 0 to n minus 1 that encapsulates all the frequencies there are, so we don't need like the rest because it's periodic?
Yeah, exactly. So what we kind of did is what we kind of just like we kind of proved the inverse discrete Fourier transform to this a little easier to understand. So basically what happened here is that you can see here, for example, we have two different cosines at two different frequencies. Our samples are at a um, has a fundamental period of 4. So as you can see, um, after our W comes around to like k equals k equal so the first one cosine with a 2 pi over 4 times 1 is going to be our like k equals 1, and then cosine 2 pi over 4 times 5 is going to be like basically k is equal to 5. So as you can tell, they're perfectly 4 apart, and when you kind of map them together, they have the exact same representation when we like put it up again when like we try to reconstruct it with our samples. So basically we are able to get all of our information um, from just those n minus ones, which is what you said. And basically it's like the same idea as like aliasing that we talked about earlier, where like um, there's like a certain minimum frequency that can represent a signal, and any more like will also just show the same samples. Um, just depending on the sampling. It's like basically aliasing, but now we're using it for our advantage. Yeah, does that make sense?
Yeah.
So yeah, I mean, you basically had the right idea. It's just reaffirming it. Okay, any other questions? All right, so as I said, we are not working in the continuous domain because that's a lot of values that we cannot store or show. So instead, how we're going to show our frequency is by ranges called bins. So basically, our frequency range is going to range from 0 to our sampling rate. And this capital X of K is our frequency representation, and it shows us how much of our signal comes from each bin. So basically, for example, if we have a sampling rate of 2 hertz, that means our maximum or our frequency range that we can represent is from 0 to 2 hertz. And if we have a big N of 8, we sample 8 times, then that means each bin will represent 0.25 hertz. So what that means is if we're in bin 1, we're going to be at 0 to 0.25. If we're at bin 4, it'll be like 1 to 1.25 is present. So yeah. So basically, okay, I guess we'll show this first. So here we have a signal that is comprised of 2 different cosine sinusoids. One is at 1 hertz frequency, one is at 0.5 hertz frequency. And then I guess the little question there is, does anybody know why it's at 2 hertz? Why we're sampling at 2 hertz? Yeah.
Because it's double the maximum frequency present.
Yeah, exactly. So that's the Nyquist rate. That's our bare minimum frequency in order to perfectly reconstruct the signal without any problems. All right, so we did the sampling here. So we sampled 8 times the values and the corresponding DFT. Don't worry about the values too much. You can calculate it if you want to, but we're just trying to get the concepts here. So basically, from these samples, we received the discrete Fourier transform. So basically, we have 0, 0, 4, 0, 16, 0, 4. So basically, each of these are going to be represent one of our bins. So yeah, can anybody tell me I guess all right, that's kind of useless question. But basically we sampled at 2 hertz, right? We sampled 8 times. So that means our bins are going to represent 0.25 hertz. So basically our first bin is 0, so that means there were 0 frequencies from 0.25 to 0. And then all right, here's a question. Can anybody tell me what frequency has a rep has 16 as has 16 as the value? What bin of frequencies it has 16?
1 hertz.
Yes, that is 1 hertz. Okay, sounds good. So we can now actually see it on our histogram. So this is what our digital audio visualizer shows, if that's what you would like to create. So it shows our histogram, and we see spikes here at 0.5 hertz and 1 hertz, which is expected. However, so if you remember, our graph here or our function here is 1 hertz and 0.5 hertz. And then you also notice that there's an amplitude of 2. So that means the 1 hertz there is even more present than the other one. So that's kind of represented here with the 1 hertz being a lot higher. However, something interesting to note is that there's actually a 1.5 hertz spike as well. So to kind of explain this is it's kind of a byproduct of the discrete Fourier transform. So the 0.5, basically everything will always be mirrored. So V1 is mirrored on itself, so it's just superimposed. But then the 0.5 and 1.5 hertz are mirrored over. So the 1.5 hertz is actually also giving information about the 0.5 hertz components. And then when you combine the 2 spikes together, because they're representing the same thing, we find that it actually has a like a presence of 1, or what's that? A presence of 2 at the uh at the 0.5 hertz region. So kind of like explaining the reason behind that a little bit more. I included underneath our equation from earlier, I included the Fourier transform for cosine underneath it. So the Fourier transform for cosine is 1/2 times um, a impulse function shifted backward and shifted forward. So basically that cosine frequency representation is split into something split 2 different ways. So that's kind of why that split happens in general. Yeah, hope that makes sense. And yeah, any questions on that section? Cool, yeah.
Okay, so that was the discrete Fourier transform. Now we're going to go over the fast Fourier transform. So people in the past, they've devised a way to reuse the discrete Fourier transform calculations to speed up the computations of the Fourier transform. So this is what we call the fast Fourier transform. And this decreases the algorithm time complexity from O of n squared down to O of n log n. And so that's a very, very big decrease. And so that's why we'll be using the fast Fourier transform. So if we go back to the discrete Fourier transform equation that Gerard explained earlier and derived, we'll see in later slides that as we decrease the number of points or the size of our capital N in our DFT, our computations become a lot easier. And so the FFT algorithm or the fast Fourier transform algorithm aims to simplify the DFT computation by breaking it down into many, many small DFTs and then reusing those calculations so that you don't have to recalculate a lot of the DFT. And then we then combine all of these small DFTs to get our final big DFT or the fast Fourier transform solution. So if we look at an example of a 2-point DFT, which is when capital N is equal to 2, or we're basically having 2 points of sampling and we're repeating that periodically, you'll see on the top left here, capital N is equal to 2, so we substitute that with 2. We then get 1 at the top, and then we can simplify our left-hand side to just be negative j pi kn. And then n goes from 0 to 1. And so that can then be condensed into just negative 1 to the power of k times n. And so as you can see, for a 2-point DFT, we actually don't need to calculate any of the complex multiplications that we have in our original DFT if n was bigger. And so what we're left with is just negative 1 or positive 1, and we don't need to do any multiplication there. So that simplifies our calculations of our DFT to no longer have any complex multiplication. And so our resulting 2-point DFT formula is no longer our input signal times e to the whatever. It's just the input signals added together or subtracted from one another. And capital X here represents, again, our output. So that was the calculation of a 2-point DFT. Now, if we extend this to a 4-point DFT, we can deconstruct this 4-point DFT into 2 smaller 2-point DFTs and reuse the outputs to calculate the 4-point DFT. So here we have an example signal on the left. Let's just say these are the 4 points that we sampled. We can break this down into 2 2-point DFTs. So if we take the first and third samples of our 4-point sample, we get this top here, this pink line. And then if we take the bottom 2, the second and the fourth sample, we get our second 2-point DFT. And then we perform a time shift of our second DFT to reconstruct our original signal. So this graph is a little confusing right now. I'm going to go over the math calculation in the next slide, which will hopefully make it clear. But basically what this middle graph is doing is we're trying to represent this original signal into 2 2-point DFT signals. And then because we need to reconstruct this into our original signal here, we need to perform a time shift, which is what this b of n minus 1 represents. Are there any questions? Okay. Yeah, so if we expand the 4-point DFT formula as we have here earlier, if we just substitute capital N to be 4, we get this formula expanded. So capital X of k is equal to x of 0 times e to the negative j 2 pi over 4 times k times 0 plus x of 1 and so on and so on and so on. If we apply the concept that we had over here, we can rewrite this equation into 2 2-point DFTs. So here our left is our first 2-point DFT. which we take the first and third signals, and we combine them. And then our second and fourth signals, we combine into another 2-point DFT here. And then you'll notice that if you look at the top equation and you derive the bottom equation, we have an extra e to the negative j times 2 pi over 4 times k times 1 term. That represents our time shift, which is this shift from here to the right here. And what the significance of this equation is that now, rather than having to calculate e to the negative j times 2 pi over 4 times k times 1 times the input signal for this signal and this signal, which has a lot more complex multiplications, we can reduce that down to just multiplying it once, which is over here. Does that make sense? Yeah.
So the 0 and 2 are easy to calculate. It's just the 1 that's relatively more difficult.
Exactly. So here, if we have our original DFT, 0 and 2 are easy to calculate, but 1 and 3 are hard to calculate because, or maybe not, that's not a very great example because 1 and 3 are not that hard to calculate. But if we imagine expanding capital N to be a much larger number, 1 and 3 would be harder to calculate than 0 and 2 if you just like simplify the exponent. So if we extract this out and calculate this as a separate DFT and then multiply the complete product, a complete sum by the e to the negative j 2 pi over 4 k times 1 once, then we reduce the total number of complex multiplications. And that makes it a lot more optimal. Yeah.
Could you repeat this like recursively? Like if you have a bunch of those and you break it in half, could you then take each subpart and break it again?
Yeah. Yeah, exactly. That's exactly what the fast forward transfer does. So here I'm just motivating a very basic example of a 4-point DFT, but you can extend this to be 8-point, 16-point, and 32-point. So basically for a 32-point, you'd break it down into 2 16-points, and each of those you break it down to 8 points, and you do that recursively. So this is a recursive algorithm. Yeah, are there any other questions? Mm-hmm.
So is the time shift possibly this investment properties?
I basically I don't
I think this is more of like a mathematical
I think it's just like the
derivation.
math.
Yeah.
So basically what's happening here is like basically you're just factoring out e to the negative j 2 pi over 4 k times 1, which basically just subtracts 1 from your exponent from there. So as you can see, was previously negative j 2 pi over 4 times k times 1. So by factoring that out, you just subtract it to 1, which makes it 0.
Mhm.
And as you can imagine, that does make it a lot easier to calculate because then that whole exponent just becomes, that whole e term just becomes 1. And then if it's 2, it'll just become
Negative 1.
It'll become negative 1.
Yeah.
It's a lot easier than calculating like 3 pi over 2. So that's why it like motivates that. So I don't think we're using any special properties. We're just kind of factoring something out.
Yeah, because we're dealing with discrete signals rather than like continuous. Any other questions? Okay, great. Yeah. Oh, yes.
Again, for what was A and B again? Like, why are we separating into A and B?
Yeah. So if we look at this graph here, we have our original like input signal, which is consisting of 4 different points. We can separate this into 2 separate, smaller discrete Fourier transforms to calculate. One of them we'll just call A, and the other one we'll call B. So this one would be A, and this one would be B. And so what this is just representing, this is the DFT of our top 2 signals here in our graph. And the second DFT represents the bottom 2 signals in our graph, or it's the second and fourth point.
Well, on what basis are we separating? Like, how do we decide like what to separate?
I can't really give you the exact proof, but the general formula is that it breaks, you break down a DFT into its evens and odd signals. So let's just say we have a bigger DFT, let's just say it's like 8-point DFT, then you take the 0, 2nd, 4th, 6th index and make that as one separate DFT. And then for the other DFT, you make the 1st, 3rd, 5th, and 7th.
So,
And you keep on recursively doing that.
yeah. So you're doing index and.
Yeah.
Oh.
Yeah, so like in general, like go to the other slide. So basically the even ones are nice to calculate because they'll all be like factors of 0, 1, -1. But then the odd ones, we factor out that one exponent, which makes it now look like an even, which makes it nicer. So it just makes things easier
Like a
to,
complex exponential.
Yeah.
You're trying to make that easy.
yeah. So by introducing a shift, the complex exponential now looks like an even as well. So,
Okay.
Yeah.
If we're like a larger DMT, instead of breaking it down recursively like outways two, what's stopping you from just breaking it into like an arbitrary number of 2 DMTs? Because if like as long as you have an even number of points and they're just like equally spaced along the unit, if you choose any 2 points that are opposite from each other, isn't there a time shift in the return into your current response?
So are you saying like breaking it down into not just evens and odds, but like breaking it down
Or
into
like say you have like if you had an 8-point DOT, you break it into 4 and 4
Mhm.
like 4 versus 2, right?
Yeah.
What's stopping you from having a 6-point DFT and breaking the 3 versus 2?
Mm.
And each one would have like a 9, even the negative 5 over 2, 5 over 8.
the problem with that is that basically after this whole thing happens, you'll kind of see it drawn out later, but you're going to perform another DFT. And at that point you'll have 3 sets, and that's kind of an odd number, so you won't be able to do DFT there. Or
Yeah.
FFT there.
The power of the FFT comes from like its recursive nature. And if you break it down, it's like more irregular. It's going to be a lot harder. However, there are existing FFT variants that you can break it down to 3s or like even 5 or like random arbitrary numbers. But it's been proven that like powers of 2s are a lot better than like non-powers of 2s. So like what we call, since we're breaking this down into 2 separate DFTs, this is what we call a radix 2 FFT. This is like going too in depth, but like to answer your question, there's also like radix 3s where you break it down to 3 parts. There's also radix 4s and radix 5s, 6 and whatever. And most optimal would be radix 4, which is where you break it down into 4 separate DFTs and you keep on doing that recursively. Yeah. It's just a matter of how optimal it is. And it turns out that radix 4 is a good bridge between parallelization and also how many operations there are. Yeah. Okay, any other questions? Yeah.
But the histogram, what does the amplitude tell us exactly? Like, I get that the x-axis will tell us the frequency, but does the height of the histogram tell us like the presence of the signal, like how much of the presence in the house or something?
It tells you like how loud that signal is. So, like if you imagine like a sound signal, if in the frequency spectrum there's let's just say a very, very big amplitude in one frequency, that just means there's a very overpowering, like very loud signal that's oscillating at that frequency, as opposed to like lower amplitudes in other frequencies that could be like noise or whatever.
Oh, so
Yeah.
it's the amplitude of the frequency.
Yes. Yeah. So like if you imagine it in a time domain, the y-axis stays the same. It's both like the amplitude for the time and the frequency domain. It's just like the x-axis changes from representing sound like a signal in time versus representing it in a frequency. Yeah. Okay, great questions. Yeah, so as I was saying, we could break this down mathematically. However, it's a lot more efficient to represent the FFT in a butterfly diagram. And what a butterfly diagram is just this diagram here. Basically, you have your 4 input signals on the left, and then your 4 output signals on the right after you perform the transform. And I'll go over why it's like ordered in this way later on, but just for now, ignore this. But here we have our 0th and 2nd, and then we have our 1st and 3rd. If you go back to our original signal, you'll see that we take our 0th and 2nd index inputs, and so that's why we order it in this way. And each of these like hourglass kind of figures, they represent one butterfly operation, which is a 2-point DFT calculation that we do. So what that would mean is like here, if we have A of n, then it would correspond to this this calculation here. So x of 0 times e whatever plus x of 2 times e whatever, that would represent this like hourglass thing. And then this one would represent the bottom one here. Does that make sense? Okay, great. And after that, we're not done. So for a 4-point DFT, to break it down into two separate two-point DFTs, we have to perform another series of calculations. So now rather than taking the 0th and second inputs, we take the outputs of the 0th and the output of the first input, and we perform another 2-point DFT. And then we do the same for the second and the third outputs. And so if we extend this, like you said, if we, let's just say, have an 8-point DFT and we want to break it down into smaller 2-point DFTs, you'll see that we have a lot more butterfly calculations. Here is just a different way of representing the butterfly unit. And what this butterfly unit represents is like, here we have 0 and 4. I don't know if you can see, it's a little blurry, but there's like arrows telling you that like 0 and 4 get added at the top. And here 0 and 4 get subtracted. And before x of 4 enters into this like DFT calculation, we have to multiply it by a twiddle factor, which is what I'll go over next. So are there any questions regarding like how we represent the fast forward transform like graphically? Okay. Yeah, so as I said earlier, the W that you see in this diagram and also in this diagram, it represents a multiplication with a complex exponential, which is also what we call a twiddle factor. So this essentially represents the time shift that we have here. And how do we calculate these twiddle factors? So for a 4-point f of t, we can look at the complex plane where we divide the unit circle into 4 points of equal angle. And this would just be like essentially the roots of unity. And it'll get you the following values. And for a general endpoint f of t, we'll divide the unit circle into n equal angles. And if we look at it graphically, or if we look at it like mathematically, it basically represents cosine of 2 pi times k over n minus j times sine of 2 pi k over n. So this is the general formula for a twiddle factor. So let me ask a question. What is this bottom twiddle factor going to be? The value. W of 1, 4. Yeah.
Was it negative 2?
Yeah. So if you look at, oh yeah, the answer's right there. I didn't even notice. Yeah. But if you plug it into this equation here, you'll see that it gives you the same answer. Okay. Great. So as I said earlier, for each butterfly unit, you'll receive 3 different inputs. So here you'll receive your first input here, x of 1, and then the second input, x of 3, and then you also have a twiddle factor that's associated with that. And then what you do is you perform A, which is x of 1, plus B, which is x of 3, times the twiddle factor. And so for all of these butterfly calculations, you do the exact same operation. So if we look at this mathematically, what this represents is x of 1 plus e to the negative j 2 pi over 4 times k times 0 times x of 3. So this is our twiddle factor. And then here we have x of 1 minus this twiddle factor times x of 3. Does that make sense? Okay. And yeah, so that's the 4-point f of t. Here I already showed you an 8-point f of t. Here's a 16-point f of t, which is even larger. There's a lot more butterfly operations. And you'll see that there's like a very regular structure, which is that like here you have the two points are like next to each other, and then they grow increasingly farther apart from each other at double the rate. And this is because, as I said earlier, we're breaking the DFTs down into evens and odds. So if we do that recursively, you'll end up with this kind of structure where we have to perform our 2-point DFTs in this kind of manner. And these butterfly diagrams will be very, very helpful if you want to do the audio visualizer track, because if you want to make a 16 point or a 32 point, we don't expect you to calculate all of this by hand. So usually you just go online and search up a butterfly diagram here like this, and then just perform those calculations. Okay, great. So that was all of the conceptual stuff regarding what the fast Fourier transform is. Now we're going to go into how we can implement the fast Fourier transform in hardware. So as you may have noticed, the main operations that we have for the fast Fourier transform consists of a bunch of complex multiplications, complex additions, and complex subtractions. So for now, for the rest of this lecture, we're going to represent our complex number in the form z is equal to a plus jb. So let's just look at one butterfly unit and break it down. So earlier I said that for one butterfly unit, we do a plus b times w and a minus b times w. And note that a, b, and w are all complex numbers. And so we'll represent them in z of a plus z of b times z of w. So let's go over the multiplication first. To break this down, we have to break each of these terms into their real and complex form. And then we perform basic multiplication using the FOIL method. And so here, if we have a sub b plus j times b sub b times a sub w plus j times b sub w, we will extend this using FOIL, and we get the following term here. And how we store this in hardware is we break a complex number down into its real and complex numbers, and then we store each of them into their separate variable or like number. So like here, we store z of b into two separate variables, one that represents only the real and one that represents only the complex or the imaginary. Sorry, not complex, imaginary. And then each of them will be their own 16-bit numbers, and then we just perform the multiplications that way. And then once we get this final term, we can add this to z sub a. So we add this to the real component of z sub a, and we add this to the imaginary component of z sub a. So this is a little tricky. So when you're multiplying two 16-bit numbers, doing fixed point multiplication, multiplying two 16-bit numbers, as I think we briefly covered in like lecture 1, it will result in a 32-bit product. So in order to in order to store the multiplication of two 16-bit numbers in full precision, we have to store it in a number that's 32-bit wide. However, we don't have the resources to be able to do this, and so we have to truncate it down back into 16 bits. So how do we do this? First, when you multiply two 16-bit numbers, the sign bit will be duplicated. And so we can essentially take out one of the sign bits and only take the remaining one. And then after that, we truncate the 15 least significant bits. So we're essentially doing like a bit of rounding in order to fit all of these, in order to fit the product into a 16-bit result. And so, yeah, do you guys have any questions regarding the multiplication? Yeah.
I'm curious because I remember I heard that multiplication is incredibly intensive, like resource consumption-wise on the hardware. Is that fine that we're multiplying up to like a 32-bit number?
Yeah, I think 32-bit is definitely like on the heavier side, but given like the size of your FFT and like whatever, a 32-bit multiplication should be, yeah, it should be doable on RFPGAs.
There are ways to like optimize it, but like using certain like tiles within that PGA. That's not really something we go over.
Yeah.
Maybe I will. But yeah, there are ways to optimize it. But for our case, like it performs fine.
Yeah.
So just to make sure, when we multiply two complex numbers in a binary representation, we're representing the real part in bits and the imaginary part in bits as well.
Yeah, so in a complex number, when we represent it in hardware, we have to break it down into its real and its imaginary components. So one variable in like your code would represent the real component, and then another variable would represent the imaginary component. So you can say like a sub real is whatever, and a sub imaginary is going to be another number. And then you perform like these like expanded multiplications, like here, to perform complex multiplication and addition.
The real and imaginary 16 bits long.
Yeah, it's like we recommend that, but you can make it however long you want. Like you could represent the numbers in 32 bits, like as Josh said, or you can represent it in like 8 bits, if you feel like that's enough information. It's just a matter of how much precision you want in your design.
Is it possible to represent them in polar form, like where you have like the magnitude? Because I was thinking when you multiply in polar form, like multiplying the exponentials, the complex exponentials, you just add them up the exponents.
I think one thing to note is like if you aren't like doing this whole rounding thing, is that as you saw, there's like multiple stages and just like the thing. So basically, your first stage you start with 16, end up with 32. Your next stage you'll multiply 32 by 32, end up with 64, and so on. So it'll get bigger and bigger as you go. If you don't like round and truncate on each step and keep it consistent, so it can like easily grow, kind of unnecessarily. But yeah, I mean it's just like if you want to play around with the sizes, it's totally possible.
Yep. Okay, yeah. So as I said earlier, multiplying two 16-bit numbers, it'll produce a 32-bit product, and we need to truncate that. So as I said, first step, because multiplying two 16-bit numbers gives you a duplicate sign bit, we can remove the most significant bit. Now, so we have bits 31 to bit 16, and then we truncate the last 15 bits. And that is essentially like some sort of rounding. And so is that it? Problem solved? Not exactly, because if we discard the last 15 bits, we're effectively right shifting the product by 15. And what that does is dividing our answer by 2 to the 15. And so our answer will actually be wrong. To fix that, we can actually leverage our twiddle factor that we have earlier, and left shift the twiddle factor by 15 to counteract what we did to truncate our multiplication when we do our twiddle factor multiplication, when we multiply our B and W. Because if you look at the twiddle factor formula, it's always going to be within the range of -1 and 1. So we have enough bits to play around to left shift everything by 15 bits and still have that fit within a 16-bit number, minus like very, very small edge cases, which you'll see in Lab 4. And so, yeah, essentially what we do is we left shift the twiddle factor by 15, and then we perform that multiplication with B, and then we right shift that product by 15 by truncating the least significant 15 bits. And that's how we get our final product. Are there any questions regarding this? Okay, great. Yeah, so just as a recap, that's basically all you need to do to implement the fast Fourier transform on hardware. So first, you need to pass in the correct inputs and the scaled twiddle factors. So scaled twiddle factors meaning the twiddle factors are all left shifted by 15 bits. Then you follow the diagrams and the unit circles. You separate the real and imaginary components in your calculations, perform B times W using FOIL, and then finally, you add that product into A, or subtract that product into A. And then that's how you calculate one singular butterfly unit. And then you repeat that over and over again for every single butterfly unit within your FFT design. So for an 8-point FFT, it would be 3 stages, and you have 4 butterfly calculations for every single stage. So 12 butterfly units in total. And this will be the basic building block of your FFT. Yeah. So we'll be releasing Lab 4 hopefully tonight. And basically what it'll cover is you'll be tasked to implement a butterfly unit. And this will be this will be very useful when you actually implement your final FFT in your capstone. And yeah, that's it for today's lecture. Are there any other questions regarding like any of the content we covered today? Yeah.
Is this the last lab before we move to the afterlife?
Yeah, so this will be our last lab, the FFT lab, but we'll have another lecture in week 9.
Yeah.
So 3 weeks from now.
But no lab attached, so at that point, we just want to hear what you're doing for your capstone.
Yeah.
Yeah.
And then I think we'll put out the capstone proposal soon.
Yeah, let's do that.
Okay.
Yeah, the capstone, we'll have guidelines,
Yeah.
for the capstone proposal soon.
Any other questions?
By around when?
I think end of quarter.
I think,
Yeah.
I think you should try to get all the labs done this quarter, so you can focus on your capstone next quarter, but, truth be told, we're not giving you a grade. If you need time, we can